I'm going to be talking about this essentially my recreation of a Deutsch's algorithm using the Google Cirq framework for quantum algorithm simulation. Um, so I'm just going to be walking through my code kind of and explaining my whole thought process. And yeah, so we can start up at the top. These are just the libraries that I imported. Nothing really special there. This next line of code, line 10, the one where my cursor is right now, isn't important to the actual algorithm. It was just I was just using it to measure runtime. So I even included a comment here. It's not necessary. I only included it so I can measure runtime. All right, so if we go down here to line 16 to 18, this is where I define my 3 qubits that I'm using. Now, Deutsch's algorithm, for the way that I'm doing it, theoretically, it only needs 2 qubits. However, the way that I define the mapping function, which I'll get into later, it required that I use 3 qubits. Yeah, but I will talk about that later on. So if we continue on, I define 2 moments down here, which are essentially intervals along the quantum circuit, which I will later define on line 26 right here, where essentially I can control in what order the quantum gates are being applied to the circuit. So I have moment 0 is equal to, I'm applying 2 X gates on qubit 0 here, and I'm also applying an X gate on qubit 2. And in case you are not familiar with quantum gates, the X gate is basically the quantum equivalent of a NOT gate, sort of. um, and then moment 1 here, I'm applying a Hadamard gate to qubit 2 as well as qubit 1. So essentially, these NOT gates are being applied first, and then these Hadamard gates are being applied. So we go down to line 26, and I've defined the quantum circuit with the 2 moments. These are my 2 initial moments. I'm going to end up adding more stuff to the circuit, but we can just start it off with these 2 moments. So then we have our function array down here. So I have the function right now set to 0, 1, which means that I've basically said that f at 0 is equal to 0 and f at 1 is equal to 1. But if I want to change my function, then I can just change the values in this array. So with Deutsch's algorithm, the whole point of it is to test whether some bit mapping function that basically maps one bit to another bit is constant or balanced. And yeah, this is basically just how I define that function. So now we get it kind of into the nitty gritty stuff here. So I'm defining this. I just called it passing function, and we take an input as our essentially our qubit x measure, which is basically going to be whatever we measure, essentially what we measure our qubit to be at the end. Now this right here isn't really necessary. In fact, I don't think I even use it in the code, but it's just a function. It's just supposed to like illustrate essentially how this bit to bit function works. And I think I was going to use it at one point, but I decided not to. So this right here is actually not necessarily needed, but it was just kind of a good representation of how the kind of bit to bit function would have worked. So if we continue on down here, we basically get into the whole mapping function, which I had to define because it wasn't actually well defined in any of the information that I read. So what I did here is I said that if the function array at 0 is equal to the function array at 1, meaning that if this is equal to this, so if it's 0, 0, and 1, 1, then I'm going to apply a Tofeli gate, which is essentially defined right here. So it's also called this CCX gate, where we use qubit 0 and qubit 1 as our control qubits, and then qubit 2 as the qubit that we're actually targeting, our target qubit. And then we append that Tofeli gate to the circuit, and then we also add on a C NOT gate between, a controlled NOT gate between qubit 1 and qubit 2. And we also append that to the gate after the Tofeli gate. And now I say, if the function array at 0 is equal to 1, so if this right here is equal to 1, obviously it's not right now, but if it were equal to 1, then I would apply an X gate or a quantum NOT gate to qubit 2, and I would append that to the circuit. Now, let's say else. So if function array at 0 is not equal to function array at 1, because that's like the other case, then it goes to the else gate, and what we do is we apply just a C0 gate between qubit 1 and qubit 2, and we append that to the circuit. And then again, if function array at 0 is equal to 1, so if this were to be equal to 1, then we'd apply a X gate to the circuit, a quantum NOT gate, and we just append that to our pre-existing circuit. Down here, I've defined a function, which is basically, I've called Deutsche circuit init. I'm not really sure why I named it that, but I guess I had my reason. And essentially what this does is, it just measures our qubit. So we're measuring qubit 1. Um, yeah, so that's basically all it does. So what it well also it also what it also does, it appends just another Hadamard gate to qubit 1 as well. So when we apply this function to the circuit down here, it's going to apply that Hadamard gate, and then it's going to take a measurement of qubit 1. And then what it does here is I print the circuit, and that gives me a very nice looking circuit diagram of the entire circuit. And then basically I just define my simulator down here, and I run the simulator, and I print the result. And it gives, and from what I've tested, it gives the desired results for Deutsch's algorithm. And then down here, this final line, again, I said this is not necessarily only included in the code, so I can measure runtime. This is basically just printing the final runtime. So that's pretty much it. Yeah, so this is essentially how I simulated Deutsch's algorithm on Cirq.